In this second lecture of Mathematical Methods for Physics, we discuss the general properties of ordinary differential equations. We begin with some definitions. An ordinary differential equation, or ODE, involves derivatives of a function y of x with respect to a single independent variable x. The equation is called linear when y and all its derivatives appear only to the first power and are not multiplied together. A second-order equation is one in which the highest derivative is y double prime. A key example is the harmonic oscillator equation, y double prime equals lambda y. Other important examples include the Legendre, Laguerre, Hermite, and Bessel equations. More generally, we can write a linear second-order equation in the eigenvalue form Ly equals lambda y, where L is a differential operator. This equation is crucial to the analysis of the so-called homogeneous and inhomogeneous second-order linear differential equations. A homogeneous equation is one of the form Ly equals 0. It is inhomogeneous if it equals some function h of x. A linear second-order ODE has then the form L of y equals h times y, where L equals a2 of x times d squared over dx squared, plus a1 of x times d over dx, plus a0 of x. We now turn to the question of intervals, normality, and boundary conditions. The interval I on which an equation is solved must be fixed in advance, since the qualitative behavior of solutions can depend on the interval itself. We say that the operator L is normal on I if a2 of x is not equal to 0 for all x in I. Points where a2 of x equals 0 are called singular points. For example, in Legendre's equation, a2 of x equals 1 minus x squared, which vanishes at x equals plus or minus 1. Hence, the operator is normal only on the open interval from -1 to 1. Throughout the course, we work with ordinary, linear, second-order equations that are normal on the interval of interest. Next, we introduce the eigenvalue problem Ly equals lambda y. For a fixed operator L, there is usually an infinite family of solutions corresponding to different eigenvalues. For each eigenvalue, all solutions can be written as linear combinations of two independent ones, because a second-order equation introduces two constants of integration, c sub 1 and c sub 2. The general solution of y double prime equals 0 is y equals c sub 1 times x plus c sub 2, with basis functions y sub 1 equals x and y sub 2 equals 1. Thus, the space of all solutions of a homogeneous linear ODE, for example, the eigenvalue problem with a fixed lambda, forms a two-dimensional vector space. To determine a unique solution, we must fix these constants by imposing boundary conditions. In general, on AB, they take the form alpha sub 1 times y of A, plus alpha sub 2 times y of B, plus alpha sub 3 times y prime of A, plus alpha sub 4 times y prime of B, equals gamma sub 1, and a second, similar equation with beta coefficients and gamma sub 2. Specific cases include unmixed conditions, where each endpoint provides one relation, the Dirichlet type, fixing y of A and y of B, and the Newman type, fixing y prime of A and y prime of B. Other important cases are periodic boundary conditions, where y of A equals y of B and y prime of A equals y prime of B, and initial value problems, where y of A and y prime of A are given. A fundamental theorem then states, for such an initial value problem, if the equation is normal on I, there exists a unique solution on that interval. The harmonic oscillator equation beautifully illustrates how boundary conditions determine possible eigenvalues. When lambda is positive, the solutions grow or decay exponentially, so only the trivial solution satisfies homogeneous boundary conditions. For negative lambda, the solutions become oscillatory, sines and cosines, and the boundary conditions restrict them to discrete wavelengths. These quantized values correspond to lambda equals minus n squared, the familiar standing wave condition. Finally, when lambda equals 0, the solution is simply linear in x, giving one unique straight-line profile across the interval. So the boundary conditions control not just the shape of solutions, but which eigenvalues, or physical modes, are actually allowed. The Legendre, Hermite, and Laguerre equations are classic examples of how requiring well-behaved, terminating series solutions quantizes the possible eigenvalues. In each case, physical or mathematical consistency turns a continuous spectrum of possible lambda into a discrete set, the hallmark of quantization. For Legendre's equation on -1 to 1, One solution is logarithmically singular at the endpoints, so regularity excludes it. If we also require a terminating power series, we get the Legendre polynomials with eigenvalues lambda equals minus n times n plus 1. For Hermite's equation on the whole real line, both solutions are regular, but demanding a terminating series gives the Hermite polynomials with eigenvalues lambda equals minus 2n. For Laguerre's equation on 0 to infinity, regularity at the origin rules out the logarithmic branch. Imposing a terminating series yields the Laguerre polynomials with eigenvalues lambda equals minus n.